And at the end, we can have question answers. You could ask questions during the lecture also by typing in the chat box, and we will relay them to Jason. So Jason, you are welcome to begin your lecture.
All right, well, thank you very much, and thank you for having me back for a second week. For those of you who were here last week, I talked about how Rees-like algebras were important in the construction that Arena and I made for counterexamples to the Eisenberg-Godot conjecture. But if you weren't here last week, I'm not going to use very much. It's going to be a relatively disjoint talk from last week. It's just primarily motivated by what I talked about last week. So the goal for this week is to study these Rees-like algebras in a little more detail and say, all right, we know that they were an interesting machine for constructing counterexamples. What can we say about their geometry? What can we say about their algebra? Can we say anything at all beyond the fact that we know, some of these basic invariants that you get from the free resolution? So the two main references are on the left. If you want, you can go to my webpage and you can get both of the copies of these papers to take a look. A little bit at the very beginning, so items 1 and 2 are still the joint work with Reina Pava, and the rest is joint work with Paolo Mentaro and Lance Miller. That is basically the content of these two papers. So I'm going to talk about the defining ideal, the graded free resolution, talk a bit about the codimension of the singular locus and what that says about when we can create smooth hyperplane sections. We can say a little bit about semi-normality, weak normality, and F-purity, and when each of those happens. If there's time, I'm going to talk a little bit about the class group and the Picard group, and I'm almost certainly not going to get to item 7 because I doubt I will have enough time. But if you want to see a little bit about the canonical module, that is in this second paper. Okay, so let me set notation. So once again, I is going to denote a graded ideal in a polynomial ring, say generated by m elements. And let's denote the standard graded polynomial ring S, say in n variables. So S is standard graded and I is a graded ideal. Then, so before I talk about Rees-like algebras, let me say just a tiny amount about Rees algebra. So the Rees algebra of I, I'll denote it as a script R of I. You can also denote it as S adjoin IT, where T is a new variable, and you think of this as living in some polynomial extension of your original polynomial ring. So if you think of the grading just with respect to T, then the Rees algebra decomposes as a big direct sum of the powers of the ideal. And so this is why, if people are interested in studying powers of ideals, they often look at this one gadget that sort of incorporates all of them together. So geometrically, these things are very nice because the projective scheme associated to the Rees algebra defines the blowup of, I guess in this case, affine n space along the variety defined by I. So it's very important in the resolution of singularities. However, the algebra here is difficult, meaning if I want to think of the Rees algebra as a quotient of a polynomial ring, the defining equations are very difficult to compute in general. And so there are many papers that handle special cases where you do know the defining equations, but for a completely arbitrary ideal, this is a very difficult problem. So let's compare that with what we decided to call the Rees-like algebra, for better or worse. So let me denote this with a curly RL of I. So the only difference between this and the Rees algebra is that you just throw in this t squared, which is sort of an artificial looking thing when you first look at it. This is again living in this polynomial extension. So let's think about what do the graded pieces of the Rees-like algebra look like if I think of just the grading with respect to t, rather than just the powers. what you get is this sort of alternating behavior where you see a copy of S, then a copy of I, then a copy of S, then a copy of I, and so on, which gives you a little bit of idea for why this might mirror some of the behavior you saw for the original ideal. So geometrically, at the moment, we don't know a whole lot about the Rees-like algebra, but the nice thing about it is that algebraically we do. So let's see if we can study the defining equations. So we make a new polynomial ring with m+1 new variables. And here I want to make sure that it's graded so that the degree of yi is the degree of fi plus 1. The degree of z is 2. So then we're going to define the surjective map, say capital phi from T to the Rees-like algebra of my ideal. So what does this do? It sends yi to fit. It sends z to t squared. And then the obvious thing to do is take the kernel. So P is going to be our ideal of defining equations for the Rees-like algebra. And by the way we've defined the grading, this is a graded prime ideal. Now, it's no longer standard graded, but we talked last week about how to fix the fact that it wasn't standard graded by doing one of these various sort of standardization or homogenization techniques. So one of the first things Irene and I were able to prove was that unlike the case with the Rees algebra, the Rees-like algebra has completely understood defining equations with no assumptions on the ideal. So in other words, P is minimally generated by two sets of generators. So I'll call one curly A. So this is the set of all things of the form yi, yj minus z times fi, fj, where I and j range from 1 to m. Remember, m was the number of generators of my original ideal. And another set of generators I'll call script b. And these are the things, if you study Rees algebras, you're more familiar with. So these are just the elements that come from the first syzygies of your original ideal. So they're the sums ci, yi such that the sum ci, fi is 0. So these are the defining equations of the symmetric algebra. You always see these in the defining equation of the Rees algebra. The question there is, are they the only ones, or are there possibly more? That's what makes it very difficult in general. So note T mod B, I guess I should say it like this. I also have to kill Z, is isomorphic to the symmetric algebra of the ideal, and the curly B are always among the defining equations of the Rees algebra. I mean, for instance, those are the equations that don't have a z in them. So of course they'll be there. The difficult part is whether they're anything else. And so the nice thing about Rees-like algebras is that these other defining equations in script A basically suppress everything else that might have been in the defining ideal for the Rees algebra. So it makes it very nice to study because we have this well-defined set of defining equations. And I'm going to refer back to this throughout the talk. I want to have two running examples just so you have something concrete to hold on to. So example number 1 is in some ways simple, but it was also very much a motivating example for us. So let's just take a principal ideal generated by a single variable in a one variable polynomial ring, about the simplest possible setup you could ask for. So the Rees-like algebra of this ideal, I could think of as k adjoint x, xt, t squared. Well, so you map a polynomial ring onto this, and you get the defining ideal. Now notice, if there's one generator, there are no syzygies, so there are no script B generators, and there's only one of type A, so this is a hypersurface defined by the equation y squared minus x squared z. And this is living inside this polynomial ring in 3 variables. And notice I'm suppressing the subscripts because there's only one subscript to worry about. And you may recognize this. So this is something called the Whitney umbrella, or some people call this the pinch point. So the only thing I want to note for now is that this is a hypersurface, hence it's Cohen-Macaulay. And this is about the only case in which a Rees-like algebra is Cohen-Macaulay. So for the second running example, let me do sort of the next most simple example. Take an ideal generated by 2 variables in a 2-variable polynomial ring. Already this gets more complicated. So the Rees-like algebra, to be explicit, is generated by x1, x2, x1t, x2t, and t squared. So by the theorem, there are going to be, well, let's see, m here is 2. So I have the case I and j are both 1, I is 1, j is 2, and I and j are both 2. So there are going to be 3 generators of type script A, and they look like the following: y1 squared minus x1 squared z, y1, y2, minus x1, x2z, y2 squared minus x2 squared z. And then there's a single relation on x1, x2. So there's a single generator of type script B that looks like x1, y2 minus x2, y1. And so by the theorem above, those are the only defining equations. These are, of course, living in this 5-variable polynomial ring, not standard graded. But it is still graded. And notice, remember, the degrees here are 1, 1, 2, 2, and 2. So you can still write down a graded Betti table for what the resolution looks like. It looks something like this. So it has projected dimension 3, regularity 4 in this sort of non-standard sense. And let's see, so there is one generator of degree 3 that corresponds to this one once you realize the y variables have degree 2. And the other 3 are all of degree 4. And then there are 4 first syzygies, 1 second syzygy for the ideal. So that's the complete Betti table. And I guess if you stare at this a little bit, what I hope you will see is that, well, this looks like a causal complex, or the Betti numbers for a certain causal complex. And this looks like the Betti numbers you might see in an Egon-Northcutt complex. And so that's sort of what motivated the idea that maybe there's some nice structure for the resolution for these ideals. But let me just record here some of the invariants so we can refer back. The codimension of P is 2, while the projected dimension of the quotient is 3, so definitely not Cohen-Macaulay. And the regularity in this non-standard sense, remember I mentioned last time you could compute this as the regularity of the original ideal plus 2 plus the degrees of the generators of the original ideal ends up being 4. And I'll recall this formula in a second. Okay, so those are the 2 running examples I want you to think of. And remember, if you remember from last time, the only case I got a Cohen-Macaulay ideal was when I started with a principal ideal. Otherwise, I'm never going to see something Cohen-Macaulay. So let's talk about what we can say in general about free resolutions. So first note that the variable z was not in the ideal of defining equations. So that means z is a non-zero divisor on the quotient. And hence, the graded Betti numbers of the quotient T mod P are going to be the same as the graded Betti numbers of what I'll call T bar, P bar, where T is just the quotient where I kill Z. And of course, P bar is the image of P in this quotient ring. So it suffices to study the graded Betti numbers after I mod out by Z. And after you mod out by Z, nice things happen. And why does that? So this is something we didn't realize at the time. But if you go back and think about the T grading on the Rees-like algebra, modding out by the variable Z is the same as killing the ideal generated by T squared in the Rees-like algebra. So this has the effect of just killing everything of degree 2 and higher. And what you end up with is something you might call a trivial extension of the original polynomial ring by I. Some people call this a Nagata trivial extension. It's the ring where you extend the ring by a module and you define the product of every two things in that module to be 0. So this is what you might call the Nagata idealization or trivialization. And the nice thing is we can actually explicitly write down a resolution of this ring. And the way you do that is you use the following short exact sequence. So I take the original generators, these script A and script B, and then I view them as elements in this quotient polynomial ring T bar. So I'll put a bar over everything when I'm thinking in the quotient. So here's the short exact sequence. Yes?
Yeah, just one clarification. The very first line on this page, is the element Z in the ideal P or is it not?
I meant to write a no. Thank you. Very good. So the middle term looks something like this. And then the last term is T mod P bar, which of course is generated by A bar plus B bar. And if I just scroll back for a second, notice when I kill Z, right, those terms in script A go away, and I'm just left with an ideal here generated by a bunch of products of variables, which makes me think I may have switched the A and the B here. Indeed, I did. Excuse me for a second. Let me fix this. That looks better. So the point here is this middle ideal is very simple. It's generated by a bunch of products of variables. So we know how to resolve this. So this is just an Egon-Northcutt complex. This one takes a little bit more work, but you can show that this is generated, or this is resolved, sorry, by a causal complex on the y variables tensored over S with F dot, where F dot is the S free resolution of the first syzygy module of my original ideal. So that's how we inherit a lot of properties of the original ideal into the resolution of this ideal. Now I'm still not done because the thing I want to resolve is over here on the right. So you lift the map from B bar mod A intersect B to T bar mod A bar to some map of complexes, I'll call it alpha, by the usual homological things. This last term is resolved by the cone of that map typically, this may not be a minimal resolution, but in our case, we show that it is. So this is still joined with the random theta. So what we prove is that cone of alpha is a minimal graded T-bar free resolution of T-bar mod P-bar. And hence, because we have all the data that describes the elements in this resolution and this resolution, we know exactly what the graded Betti numbers for T-bar mod P-bar are, and then by the earlier remark, we know all of the graded Betti numbers for T mod P. So let me just recall what we can say. So we can say that the degree of the defining ideal is 2 times the product of the defining equations plus 1, the regularity of, maybe I'll just say of P, is the regularity of the original ideal plus a correction involving the degrees of the original generators. The projective dimension, let's say of the quotient, is the projective dimension of the original quotient plus the number of generators minus 1, and the codimension is exactly m. And so I need to make 2 things clear. Notice this says, again, we're Cohen-Macaulay if and only if n is 1. So here you should think about running example number 1, where I took an ideal with just 1 generator, and I ended up with a hypersurface. And up here, I was a bit fuzzy about what I meant here. So here, now we can say this is true so after some homogenization. And if you're not clear what that means, you can go back and look at my talk from last week. Okay, so at least we understand a lot about the resolution. We know a lot about these invariants, and this was sufficient to give the data needed to prove that these were honestly counterexamples if I take the right ideal and plug into this machine. So now the main question I want to talk about for today is, what can I say about the geometry, the singularities, anything like that for these rings? So this is item 3. So we'll start by talking about the singular locus. And maybe I'll just state our first main theorem. So this is joint with Powell-Mentaro, Lance Miller, and myself. So this is just going to be MMM in the future. Suppose that I is this graded ideal in the polynomial ring. Assume that the underlying field is algebraically closed, that the characteristic is not 2, and set X to be, for the moment, the affine space associated to the Rees-like algebra. So then, codimension in X of the singular locus is precisely the height of the ideal we started with. So in other words, for any prime ideal, Q in the prime spectrum of the Rees-like algebra, such that the height of Q is strictly less than the height of I, when I localize at Q, this is regular. And moreover, this was one of the things we were most interested in. This is true of this sort of non-standard graded quotient, T mod P. I really am interested in the standard graded things after you homogenize. And the original homogenization that Arenas, Peva, and I came up with messes up the singular locus in general. But this prime standardization that I mentioned last time plays nicely with the singular locus in the sense that this is still true for the prime standardization I talked about last week. but we also give examples to show that this is not true for what we called step-by-step homogenization. And if you weren't here last week, the prime standardization, the idea here is just take a variable of degree d, add a whole bunch of new variables, and replace that degree d variable by something very general, a form that's very general in these new variables. And if you take enough new variables, this works. So once we understand the singular locus, I can start saying, all right, maybe I can take hyperplane sections until I get down to something that's smooth. And then maybe I can even hope that I could come up with smooth counterexamples to Eisenberg-Godot conjecture. Well, we can't, and I'll explain why. So because we understand the singular locus, we can precisely describe for which ideals does the prime standardization of Rees-like algebra have a smooth hyperplane section. We can describe which I give a Rees-like algebra, and I'll just put maybe a star here to mean I mean the prime standardization of that Rees-like algebra that is smooth, or that has a smooth hyperplane section. Well, but I don't want to lose the information of the resolution, so I want a smooth hyperplane section that has the same Betti table. And so here, that's where knowing the precise depth of these rings was very important. So once again, suppose that the field is algebraically closed. Here I have to assume the characteristic is 0, and that I is this graded ideal as before. So let's let X denote the projective variety obtained from some prime standardization of the Rees-like algebra of that ideal. And so what we do is we prove that the following two things are equivalent. So first, that there is a regular sequence of general hyperplane sections of X such that the resulting variety is smooth. And so that's equivalent to starting with an ideal that defined a Cohen-Macaulay ring. And so at this point, you can sort of see why we can't come up with counterexamples, because I can't make the regularity of a Cohen-Macaulay ideal that bad. So if I go back to my running example, number 2, right, I was generated by 2 variables, so that's certainly a Cohen-Macaulay quotient. And the Rees-like algebra had this Betti table that we defined before. It's not Cohen-Macaulay, but it does have a hyperplane section that is smooth, that has the exact same Betti table. So I know that there is a smooth variety with exactly this Betti table out there somewhere. On the other hand, we can say that, well, all such smooth varieties satisfy the Eisenberg-Godot conjecture. So we cannot come up with smooth counterexamples this way. That does not say that all smooth varieties satisfy the Eisenberg-Godot conjecture. It just says all the ones I can create this way satisfy the conjecture. So no hope for finding counterexamples this way. Okay, so that at least rules out one avenue for finding nicer counterexamples, but maybe we can continue to say some nice properties of the Rees-like algebras. So let me say a little bit about semi-normality, weak normality, and F-purity. So as I mentioned before, it's obvious that in general, Rees-like algebras are not co-McCullough. It's also obvious that they're not normal. So these are sort of maybe the next best properties you could hope to happen. And let me just make a few definitions, as I'm not sure everyone is familiar with some of these notions. So for an extension of rings, say A to B, reduced rings, a subextension, say A includes in C into B, is called subintegral if it is an integral extension, if it induces a bijection on prime spectrum, and it induces an isomorphism on residue fields at all points. And maybe I won't write it down, but weakly subintegral is defined similarly, where you only ask for purely inseparable extensions on residue fields rather than isomorphisms. So the semi-normalization I'm going to write A upper Sn of A is then the unique largest subextension inside the normalization of A, which is subintegral. And similarly for weak normalization. And then you define A to be semi-normal. If it is equal to its semi-normalization. So it is itself the largest subintegral extension of itself inside the normalization. So in particular, this tells you that normal rings are always semi-normal, and semi-normal rings are always weakly normal. In general, these two implications are not reversible, but this one is an equivalence in characteristic 0. Right? Because this is the thing that referred to purely inseparable extensions, so that's not a problem in characteristic 0. So semi-normalization is sort of a nice, maybe I'm not asking for the ring to be completely normal. And maybe the other thing I should mention here is running example number 1, right? The pinch point or the Whitney umbrella is a classic example of a semi-normal singularity. So we saw this originally and we said, hey, if the simplest Rees-like algebra is semi-normal, maybe we can ask how often it happens that the Rees-like algebra is semi-normal. And so we were able to prove the following theorem. So suppose I is this graded ideal inside the polynomial ring over the field K. And once again, we have to assume the characteristic is not 2, as strange things happen in characteristic 2 for the Rees-like algebra. Then the following are equivalent. So number 1, Rees-like algebra is semi-normal. Number 2, Rees-like algebra is weakly normal. And number 3, the ideal I started with is radical. So a lot of the time, if you start with a reasonably nice ideal, say a prime ideal even, and you take its Rees-like algebra, you will end up with something that's not normal, but it will be semi-normal. So this applies to both of the two running examples, since both of those were prime ideals, hence radical ideals. So maybe I should write that down. Examples 1 and 2 are semi-normal. However, I don't think I can say this after doing, say, one of these prime standardizations. We don't really know whether normalization is preserved under that process. Let me also mention that you could try to ask, well, does this same sort of behavior work for Rees algebras? And the answer is no. So compare this result with Rees algebras. So I'm going to write down a monomial curve. So consider the map from kxyz to k adjoin v that sends x to v to the 9, y to v to the 10, and z to v to the 13. Call this map psi, and let's let J be the kernel. So you can check that this is the ideal of 2 by 2 minors of the following matrix. So it's prime, and hence radical. So that means if I were to take its Rees-like algebra, it would be semi-normal. On the other hand, you can check, say, with McCullough 2. There's a nice package that will let you check this, that the Rees algebra is not semi-normal. So we don't have as nice of a result for Rees algebras. This is something that's sort of nice for Rees-like algebras. And maybe I'll also mention, if you're not familiar with semi-normal property, there's a very nice survey paper by Marie Vituli, where you can read a lot more about semi-normal properties and weakly normal properties. And that was where I learned a lot of this material. Okay. So that's sort of the story for the semi-normal and weakly normal properties. Now you could ask, all right, now that we know when they're semi-normal, could I come up with semi-normal counterexamples to the Eisenberg-Godot conjecture? And the answer is, well, no, because I don't know of radical ideals that have large regularity. If you can give me a radical ideal with large regularity, then maybe I could. So what can we say about F purity? Well, in positive characteristic, F split rings are weakly normal. So it makes sense to study when these Rees-like algebras are F split. So let me just set some notation. So assume the characteristic now of K, which is P, is positive. And for the moment, let R be a K algebra. Then the Frobenius map is the map with a ring endomorphism from R to R that sends an element to its pth power. Or if you prefer to think maybe when R is a domain, you can identify this with the inclusion of R into a set of pth roots that sends an element to its pth root. If F is split, sorry, that if shouldn't be there. So F is split. Let me start over. R is F split if this map splits as a map of R modules. And in the reasonably nice setting when R is F finite, so when R is a finite module over itself via this map, or in other words, that R to the 1 over P is a finitely generated module over R, F split is equivalent to being F pure, where you just ask that this map is pure as a R module homomorphism. In other words, then you tensor with the identity map on any module that stays injective. Okay, so when are Rees-like algebras F pure or F split? So once again, we have to avoid characteristic 2. And we show that if I is radical, then, well, the F split property is preserved by going to Rees-like algebras. So S mod I is F split if and only if the Rees-like algebra of I is F split. Now, I rather like this result because this, in a way, gives you another machine for coming up with F split rings. So for example, it's well known that if I is a square-free monomial ideal, well, of course, S mod I is radical, but it's also F split. And therefore, the Rees-like algebra of that ideal is F split. But notice the Rees-like algebra is a domain, whereas the quotient S mod I was merely reduced. So it's a nice way of creating F split domains. Now, you could also say, well, let's compare this with what happens for Rees algebras. If I have a radical F split ideal, I take its Rees algebra, is that still F split? And it took me a little while, but there are counterexamples to that statement. So I'll just say there are square-free monomial ideals such that the Rees algebra is not F split. So again, this is a nice property that Rees-like algebras have that Rees algebras do not. Okay, so I think the last thing I'm going to have time to talk about are class groups and Picard groups for Rees-like algebras. And one of the reasons I like thinking about this is because there isn't a lot of examples in the literature of computations of class groups for non-normal rings, although you can certainly make the definition in that setting and see what happens. The other thing I really liked about this is a lot of this follows from a very simple observation that I'm somewhat embarrassed we didn't notice sooner, was that one way to think about Rees-like algebras is via pullbacks. So the Rees-like algebra fits into what's called a Milnor square, or if you prefer, just a categorical pullback diagram. It looks something like the following. So Rees-like algebra shows up over here. Remember, it embeds into this polynomial extension of the original polynomial ring, but it also surjects onto S mod I adjoin T squared. This, of course, surjects onto S mod I adjoin T. And of course, we have the obvious inclusion going this way. So I claim that you can define the Rees-like algebra as the pullback of these maps of rings. And once you do that, you get sort of an easy way of calculating Picard groups. So the Picard group, pick of R, is the group of invertible fractional ideals modulo the principal ones and, well, probably the setting most people are used to is the case when R is normal. And when that happens, the Picard group is a subgroup of the class group. But that's not going to be the case here. And so from the Milnor square, there is a standard units pick exact sequence. Which makes it very easy to compute the Picard group, at least in a lot of cases. So what does the Unix pick sequence look like? It looks something like this. So this is an exact sequence of groups. So it starts with the units group of the Rees-like algebra to the units groups of the things on the two diagonals, to one more group of units. Sorry, I have to squeeze this in here. And then the second row are just the Picard groups of those rings. I'll have to go to a third line here. And so it's not so hard to analyze this exact sequence, at least in some reasonable settings. And so what we were able to prove is that if I is any graded ideal, then maybe not so surprisingly, because the normalization is so nice, the Picard group is trivial. But this only happens when I is radical. So once again, this sort of recurring theme that Rees-like algebras aren't so bad if you start with a radical ideal keeps coming up, right? If they're radical, you get a semi-normal variety, you get something with a vanishing Picard group. If you started with a radical F-split ideal, you get an F-split Rees-like algebra, etc. And let me just switch windows really quick and show you what this says about oops, that's not the window I wanted. What this says about geometry. So here is the pullback diagram that I just mentioned. So dual to that is a push-out diagram of the corresponding varieties. And so I've drawn here the case for the Whitney umbrella, or the pinch point. So that's the one in the upper left-hand corner. But you can sort of imagine this picture in general for an arbitrary Rees-like algebra. And what you have is you have the original variety, V of I, and then you take a product with just an affine line. You think of a 2-to-1 map where you sort of map a point with, or you identify 2 points along the V of I cross A, and then you sort of do this gluing map. And so what the Rees-like algebra, or the affine variety it corresponds to, looks like is it looks like affine space, except on this subvariety where you've done this 2-to-1 gluing. And so in general, that I think helps answer a lot of questions about what Rees-like algebras look like and why they're so nice. They're really nice and essentially flat off of their singular locus, and their singular locus is determined under this gluing construction. Okay. So that's all I wanted to say about Picard groups. So let me say really quick what I can say about class groups. So I need to be a little bit careful what I mean when I say class group. So let's denote CL of R for the divisor class group. Of the domain R. Some people might prefer to call this something like the codimension 1 Chow group. Since I'm not assuming that R is normal. So what I mean here is that this is the quotient div R mod prin R, where div of R is just the set of formal sums of NP bracket P, where P runs over the height 1 primes in this domain. And notice the fact that if R were a normal domain, where most of us are more comfortable, well, then we get that R localized at Q is a DVR for all height 1 primes. And so the usual notion of linear equivalence works just fine there. But in general, R localized at Q is, well, it's a one-dimensional domain. So what you have to do is you say, well, what if I take a non-zero element in R, you define the order at Q of X to be the length of RQ mod X RQ, which since RQ is a one-dimensional domain, this is then finite. And you define the map div R from the fraction field to div R that takes a quotient and maps it to the sum over all height 1 primes Q of the order of X minus the order of Y. And so then the linear equivalence you're used to is just given by the image of this map. So that's how you can define a class group even if your ring is not normal. And maybe I'll just remind you, one of the reasons you might care about class groups is that when you're normal, R is a UFD, if and only if the class group vanishes. But again, in our setting, we're not necessarily normal, so I can't rely on this. But the most general result that will give us information about the class group of Rees-like algebras is the following. And this is something we suspect maybe will not be a surprise to the experts, but we could not find this in the literature anywhere. So let's let R be a Noetherian, universally catenary domain satisfying Serre's R1 condition. So when I localize at all height 1 primes, I get a regular domain. Let's let R to the n denote the normalization or the integral closure of R. Then, if I want to compute the class group of R, it suffices to compute the class group of the normalization. These two maps, these two groups are isomorphic to each other. And so as a very quick corollary, if the height of I is at least 2, well, we know at this point, because we know the codimension of the singular locus, the Rees-like algebra will satisfy Sayre's R1. So I can apply the theorem and get that since the normalization of the Rees-like algebra is just this polynomial ring, which is itself a UFD and therefore has vanishing class group, that the class group of the Rees-like algebra, just like the class group of a polynomial ring, is 0. On the other hand, Rees-like algebras are almost never going to be UFDs. So you get a lot of examples of rings for which the class group vanishes, but they're not UFDs. And so maybe I'll just put in parentheses here that we needed that the height of I was at least 2 to guarantee that the Rees-like algebra satisfies the R1 condition. The other case, going back to my running example number 1, where I took the Rees-like algebra of a single variable, this was a hypersurface. So in particular, it was Cohen-Macaulay, which means you satisfy Sayre's Sn condition for all n. So in particular, you satisfy S2, but you're normal when you satisfy R1 and S2. And if you satisfy S2 and you're not normal, you can no longer satisfy R1. So I can't apply the theorem in the hypersurface case, but for basically everything else, we can show that the class group vanishes. And remember, I said that in general, the Picard group is a subgroup of the class group. So here we get a bunch of cases when that's clearly not the case, that the class group vanishes, but the Picard group does not. Okay, I think that's maybe a perfect place to stop the talk. So I'll thank you for your attention.
Thank you, Jason. We are open for questions. If you have questions, you can open your microphone and ask question directly.
I have a question.
Sure.
Hi, Rena.
So in that Milner square, what is the leftmost vertical map? Where does IT map?
This one?
Yes.
So it maps to 0.
Oh. Okay, thank you.
You're killing essentially, I guess, the odd degree parts.
Okay.
And then you're killing I in the even degree parts.
Right, yeah.
But there was only I in the odd degree parts. So it just goes away.
Okay, good. Thank you.
So the Rees-like algebra is very rarely Cohen-Macaulay.
Correct.
What about its Buxbaum property or generalized Cohen-Macaulay property when the base ring is actually a local ring?
We did not study the Buxbaum property, so I don't know an answer for you.
Yeah, because the singular locus, it has co-dimension height of I in many of these examples.
Yes.
So if you are working with a M primary ideal, then on the punctured spectrum, it will be Cohen-Macaulay. It's regular, and that's one property we want from Buxbaum rings. Right?
Mm-hmm. I'll think about that. I don't know.
It could be. I mean, it has I think, good chance of being Buxbaum.
Yes, it does.
Yeah. Because one has to calculate the, for the ordinary Rees algebra, one knows how the local cohomology modules, what are the graded components of local cohomology modules. But in this situation, I suppose it could be even easier to calculate local cohomology modules, and that may help in Buchsbaum property or computing depth. And
Hi, actually, I have a question in a similar line of thought. First of all, since your setup from the beginning has always been the graded ring and a graded ideal, what is known when the ring is a local ring to begin with? What is known about the Rees-like Algebras?
A lot of these things would go through, for instance, the resolution and the defining equations. That doesn't really depend on it being graded. There are a few places where I need it. So any of the calculations of like degree or regularity certainly depend on the grading. I think we used the grading to determine the units group when we computed the Picard group. So I needed to know exactly what the units groups were. So I probably needed it there. But you're right, you can absolutely define Rees-like algebras in a much more general context where S isn't just a polynomial ring, it's an arbitrary ring. And I is some ideal in that ring. And primarily we didn't study it because we didn't have a lot of motivation for thinking of it in this more general context, but you certainly could. And maybe there are other applications. It seems to be a nice machine for making examples that have very specific properties you're looking for.
Okay. Yeah, because
especially
it's like, when we have a local ring set up, we kind of concentrate on ideals which are primary to the maximal ideal. And in that case, of course, we lose that condition that the ideal is a radical ideal. So, of course, we lose a lot of information because I'm seeing many results which say that, the ideal being radical is if and only if the ring having good properties.
Yes.
Of course, we lose those things, but then I want to see how much further we can explore it because the graded components now are very much simplified as compared to the research.
Oh, and I meant to mention earlier, someone, I forget who, had asked last week where these things came from. So that was this paper by Joseph Becker from 1976 that I came across. And among other things, down here, he defines this ring here that's a local version. So it's kind of like what you're thinking about. This is a power series ring rather than a polynomial extension. And he proves that the defining equations have lots of generators. And that's really all he was using. He wanted a prime ideal with fixed height and fixed multiplicity, but with lots of generators. And so he credits this example to Hochster. But that was our motivation for defining these things more generally.
Yeah, Ravi Rao, you want to ask some questions? Your video is open. Right.
Sir, he is muted.
Okay.
Professor Ravi Rao, you're muted. Please unmute yourself.
Yeah, I like the talk very much. I'm sorry I missed the last one. It has many interesting questions which can be asked. And I, in fact, already asked my student to look at it, one of my students.
Yeah.
It's mostly, my questions are mostly concerned with the K-theory aspects of these rings.
Ah, okay.
Yeah,
I probably won't be able to say much.
Yeah. So, but anyway, you already drawn the Milnor square and already told us some things about it, which will help us. So various things like that.
Yeah, so that's in the second preprint I mentioned at the beginning.
Right, MMM. Okay.
Yes.
This Becker's paper, where is it exactly? I could not find which journal.
It's a still preprint, but you can find it on my webpage.
Oh, it's okay. All right, thank you. Yeah, nice talk.
Thank you.
Are there any other questions?
Yeah, Anant here. I don't have a question, but just a comment. I mean, I really, again, enjoyed this talk as much as the last one.
Thanks.
Yeah, and I mean, there were two questions I had, but then you answered them during the talk. One is it related to the idealization? And second is there a pullback somewhere? Right, you answered both those questions.
Oh, great. So I can't take credit for the idealization. Maria Rossi was actually the first person to point that out to us. But we were sort of using it implicitly when we wrote down the resolution.
Okay. Yeah, no, but that yeah. I mean, when we, I was talking to Vivek about it, and then when we looked at it, it looked like the idealization was there.
Mm-hmm. It is as a quotient.
Yeah, as a quotient. Yeah, and then the fire product is how what the pullback diagram is. We were thinking about it as a fire product. It seemed to be in there somewhere.
Mm-hmm.
Yeah, very nice talking. Thanks.
Thanks.
All right, I guess we have no other questions. On behalf of all the people in the audience, I want to thank Jason for giving us a nice overview of this very interesting object, Rees-like Algebra, and also the last talk on how they show up in the Heisenberg-Goto conjecture. Thank you very much, Jason.
Thank you very much.
Talk. Yeah. We'll close the meeting for today, and we meet on next Friday. Thank you very much.